Hey everybody, let's try another example using Newton's second law for rotation. So this time, let's say we have a pendulum. So it's a slender bar like this. And let's just say it's rotating about a hinge at point A. I'll just call it point A. So you let it go from rest, it's gonna have some kind of angular acceleration as it swings. What is this angular acceleration? Let's solve for that. Okay, so what do? Draw the free body diagram. So here's the slender bar, all the forces acting on it. There's weight acting at the center of mass. So let's say it's a bar of mass m. So let me jot this down. So it's a slender bar of mass m, length L. And if we look up in that table with different moments of inertia, we find that a slender bar rotating about its own center of mass, the moment of inertia is 1/12 ml squared, about the center of mass. Okay, so it has weight here. And then see there's this hinge at point A. So there's some reaction normal force at the pin. Not sure what direction. So let's say I pick coordinates. So I'm just going to pick coordinates somewhere. So I'll just say there's some x component of the normal force and there's some y component to the normal force. I'm not sure which way it actually is pointing, so I just broke it into two components. Okay, so there's the free body diagram of the pendulum. And you can, right, you know how to do this kind of stuff. Some forces in x, some forces in y, no problem, right? Some forces in y, let's see. Now, let's practice using Newton's second law for rotation. So that's the new one. Let's sum torque. Let me just move this out of the way. So let's sum torque about wherever you want. So where would you like to sum torque? About which point? Here? Here? Up to you. So if we just walk through, if you sum torque about here, let's just practice. If you sum torque about the center of mass, here, then what do we do? Okay, so I have to specify some angle over here. Let's just call this angle theta. So let's say we know this angle is theta. So where is that in our picture? So that would be over here, right? So what is the torque about this point by this force? If you look at it, what's the lever arm? Right here's the lever arm, right? So how far is this? Let's see. Here to here is L over 2. And this is opposite the angle. This is adjacent to the angle, right? So here to here has got to be L over 2 cosine theta. So I'm going to write L over 2 cosine theta times nx. And that would cause torque which way? Up from this point, this way, right? Clockwise. Which is, I pick coordinates like this, which means z is out of the page. So this force will create a torque into the page, which is negative. So I'm going to put a minus sign right here. So this is negative in the negative z direction. Okay, what's the torque by this force? Look at this lever arm right here. How far is that? Here to here is L over 2. Here to here is opposite the angle. So that's L over 2 sine theta. L over 2 sine theta times ny, and that would create a torque this way, which is the positive z direction. So this would be positive. Okay, now what's the torque about this point due to this force? 0. So that's it. Some torque, there's only the 2, so this part of the equation is done. The other side of the equation equals I alpha. Which I is this? Because we sum torque about the center of mass, then this moment of inertia is about the center of mass, which is 1/12 ml squared. Okay, so that's Newton's second law for rotation. Let's practice if we sum torque about a different point. So let's say we sum torque about over here, point A. Okay, so what's the torque about point A by this force? Nothing. Right? What's the torque about point A by this force? 0. So there's only torque due to this force. So what's the lever arm? Right here, right? See how this force is acting along this line. So the lever arm is right here, which is L/2 sine. Okay, and then that will create times mg, which creates a torque this way around point A, which is in the positive z direction. So this is positive. And then that's it, equals I alpha, which I? Because we sum torque about point A, this moment of inertia has to be about point A. Now, what is the moment of inertia about point A? About the center of mass, it's 1/12 ml squared. But about the end, let's say over here, what is it? More or less? About the center of mass, it's a minimum, right? So that means it's about the center of mass plus extra, right? So how much extra? The mass of the bar times the distance between these two parallel axes squared. So the distance between the two parallel axes squared. How far is this? L/2. Okay, so this goes here. Okay, so that's how you would use Newton's second law. And then for this particular problem, let's say, which of these two do you want to go with? I think, how about this one? Seems easier, right? So mg L/2 sine theta equals, this is 1/12 ml squared plus 1/4. 1/12 plus 1/4 is 1/3. Okay, so then just put this in the denominator, and then you got alpha. All right, so take this in the denominator. Okay, things cancel, like m, mass cancels. Let me write nicer. Mass cancels, and then there's L and L squared, so this will be 3g sine theta over 2L. Okay, so that's it. All right, so keep on practicing this Newton's second law for rotation, and I'll see you on the next video.